to say hello to everyone and to welcome into the new academic year. Hopefully it will be productive, pleasant. Happy new academic year to everyone. And you always want the first occasion to be special. Today is the first colloquium of the academic year, and I believe it is very special. Actually, Josh and I almost killed each other over who would introduce Cliff. I convinced him through my seniority that I should.
It's the opposite of my memory.
but seriously, it's a very special delight to have Cliff here because he belongs to scientists who move science forward. I don't know what your view is, but what I see, at least in my field, is that there are only few people here and there who move things forward, and many others, just write papers. So it's a tremendous pleasure to read these papers. I highly recommend. And they are extremely diverse. They are all on subjects such as cosmology, astrophysics, formal field theory, and so on and so forth. He's probably best known for putting inflationary paradigm on a solid footing of quantum field theory. Effective field theory of inflation is attributed to Cliff and his collaborators, which is one of the major, mainstream directions these days. But there are also many other very interesting papers that he has written. Today, the biography is that he got degree from Yale, I believe.
From my
a bachelor's degree, and then from PhD from Harvard.
Right.
Yeah. So at some point we tried to hire him, and we were delighted to the prospect of having him here. But he had relatives in California. So verged in that direction. That ended up to be good for him. He's a professor at Caltech these days. And the subject he's going to talk about, the unification through amplitudes. This is a different view of what the fundamental theory might be, whether it should be quantum field theory for which you would get particles, or you could start from amplitudes and then get everything else from it. And it's a very interesting approach that, again, Cliff is a leader of, and he will tell us about that.
Great. So first, thank you very much, Greg, for the very charitable introduction, and thanks to Josh and the Colloquium Committee for inviting me here today. My talk today is about an ongoing effort in theoretical physics dedicated to the study of scattering amplitudes. So just to remind you, a scattering amplitude is nothing more than a transition amplitude, exactly like the ones that you would have computed in undergraduate quantum mechanics. In this context, it describes the dynamics of particles interacting through scattering. So I think it's quite well appreciated that scattering amplitudes are kind of a critical bridge between theory and experiment. In fact, we at a pragmatic level calculate scattering amplitudes in order to make predictions, right? After all, you compute an amplitude, you square it to get a probability. A probability is some prediction which you can then verify or rule out empirically. Now, what's less appreciated, and what I want to talk about today, is how scattering amplitudes are actually endowed with their own rich and beautiful theoretical structures that are actually completely worthy of study in and of themselves. And perhaps more importantly, these structures can actually tell us new things, I believe new things, about very old theories. So this includes theories like Einstein's theory of gravitation, theory of the strong interactions. These are kind of aspects of the actual standard model that describes our world. So to me, that's in part what makes a lot of this so fascinating. These theories have existed in some cases as much as a century, but we're still learning new things even in the last decade, which I want to tell you about. Now, if you know anything about this kind of program, it has almost an infamously steep learning curve, because the kind of starting position to tackle problems is to calculate. We calculate scattering amplitudes, and as such, it can sometimes have a lot of kind of technical complexity and subtlety, and you can lose track of the forest for the trees. So my job here today is to not let that happen, and I'm going to focus, for me, especially given my understanding that the audience contains non-theoretical physicists, non-high-energy physicists, that I want to kind of convey what I think is the big picture question, which I think amplitudes can help us answer. And it's a question in physics which is, well, kind of undeniably grandiose, and that is what defines a theory. So if you ask someone this on the street, they'll say, oh, theory is defined by an equation of motion or let's say Hamiltonian, or Lagrangian. You have very smart people here. Any old Joe with an advanced degree in the physical sciences will say that obviously it's defined by something like a Lagrangian. So, and that's of course a fair answer. What do we do in classical mechanics? We define an action, which is some integral over a Lagrangian, which is itself a function of some set of coordinates which describe the degrees of freedom in our system. Now, of course, at the risk of stating the obvious, each of these equations is just some coded language for a physical assumption. The very first line, the statement that we have an action at all, encodes locality and time. After all, when we talk about a Lagrangian, it's a function of one time and one time only. We don't integrate over 17 different times, just one time. That's an assumption about the system. Second, we have other assumptions like, say, rotational invariance, which we kind of hard code into the formalism. And then everything not fixed by principles, physical assumptions, or actually free parameters that we measure, say, in experiment. Okay? So it's a general fact about theories, which is that if there is some set of parameters which are not fixed by theoretical consistency, or if you like, some first principles logic, then by definition they can take on any values, then we measure them in experiments. Okay? Things that don't satisfy that are predictions, which we check in experiments. Now, when we upgrade to the kind of modern picture, which is called quantum field theory, basically the same story applies. Here, quantum field theory is just the name we give for the union of quantum mechanics and special relativity, the modern picture for how the world works. Here, we upgrade to locality and spacetime, so we integrate an action over spacetime. And we upgrade to Poincare invariance and Lorentz invariance. And then again, everything not fixed by anything, we just measure in experiments. Right? So the essential workflow is basically the same. The 19 plus parameters of the standard model are just quantities not fixed by physical principles. That's why we can measure them, and that's why they could have taken on different values. So this is just a long-winded way of getting to the essential point, which is that Lagrangians, Hamiltonians, equations of motion, our usual starting points for theories are actually not the end-all and be-all. They're intermediate objects which take us between some set of physics principles to some set of observables, which for the purposes of this talk will be scattering amplitudes. Now, if I had to summarize what this program is about, the scattering amplitudes program, which is sometimes called the modern scattering amplitudes program or modern S-matrix program, it's essentially to cut out the middleman, to go directly from physical principles to the amplitudes. And at face value, this should seem, well, imprecise, and at least maybe wildly optimistic that you could do this. But as I will show you, this is a mathematically, completely, absolutely precise mechanistic procedure, which lets you not only learn or relearn about old facts about quantum field theory and theories that describe our world, but also determine and learn about new structures which to this day have absolutely no explanation from a Lagrangian or symmetry point of view. Okay, so we can actually learn new things also. Before I do that, I want to address a fair question you might have now, which is why bother? Okay, we've used Lagrangians, Hamiltonians, they obviously give us immense insight, and we can do calculations with them and we get the answers and the correct answers. Why bother with any extra formalism? And really the heart of it comes down to the way that we actually compute observables, typically in quantum field theory, which is using things called Feynman diagrams. So depending on your kind of proximity to theoretical physicists, you may know a little bit about Feynman diagrams or nothing. So I'm going to assume you know nothing and explain the basic gist of what a Feynman diagram is. So this is a mural that's actually in our main lecture hall of our fearless leader, Richard Feynman, long live. And he's wearing his usual Caltech regalia and a staff, which we're all given, of course, from professors. This staff contains in it a Feynman diagram. And a Feynman diagram does double duty. Okay, the first thing it does is it is a picture of the process we care about. So here I care about an electron and a positron coming together, forming a photon, labeled by gamma, which then disintegrates into a muon and an anti-muon. Okay, so that's the first thing it does. It just tells us what we're asking about. Of course, we as physicists care about equations. The second thing it does is actually give, it's a code for an actual expression, a mathematical function. Particularly each of the elements of this object, each vertex and each line, actually is associated with a mathematical expression. And when a physicist sees this diagram, the rule is to multiply those expressions together to get some big expression. That big expression is what this Feynman diagram is equal to. So this is actually just an equation. And then we sum over all Feynman diagrams to give some bigger expression, and that object is the scattering amplitude. So this is just the mechanistic way by which we compute essentially probabilities in the modern picture. We draw diagrams like this and then turn the crank. And the reason why it's so efficient is that it's easier often to draw diagrams than to write down all these distinct terms. Okay, so this is a very mature, robust, and most importantly, quantitatively successful procedure, the use of Feynman diagrams in quantum field theory. We could go on and on about it. We teach, of course, a whole course in quantum field theory. I'm sure you do too also. I'm just going to mention one kind of flagship calculation, which is very well known, which is G minus 2, or the anomalous magnetic moment of the electron, which very famously agrees with immense precision between theory, which is computed through Feynman diagrams, and experiment. Okay, so there's any number of other successes I could mention, but I just want to point out that this is astoundingly precise and a correct theory by any measure scientifically. Okay, so in other words, I'm not saying Feynman diagrams are wrong. They're just absolutely correct, and they give the right answer. But in spite of that, I want to point out the fact that there is a downside, which is that but for the simplest processes of just maybe two particles interacting, when we just get a little bit more complicated, the equations themselves become immensely complex. Okay? And to show you this, I need to introduce some of the characters that will be kind of critical for my discussion. So let me do that here, in case you're not fully primed with these kinds of concepts. Let's take the proton. Hopefully you know that the proton is not a fundamental object. It has constituents inside it. It's made up of subatomic particles called quarks and gluons. And roughly speaking, you can think of the quarks, a proton as kind of quarks bound together by force carriers, which are called gluons. And in fact, there's a very close analogy between gluons and photons. Okay? Just like the photon, the gluon is massless and spin 1, so it has intrinsic spin. And again, much like the photon, the gluon is something that can be polarized. You can left polarize or right polarize. And in this talk, I'm going to talk about a quantity called helicity, which will be plus or minus, and that just means left or right polarized. Okay, so when I talk about gluons and helicity, I'm really just talking about whether they're polarized in one direction or the other. Okay. Now, if you look very deep inside the proton and think about very high energies relative to the proton mass, you can actually talk about processes that just involve gluons scattering amidst gluons. And these are processes that are actually relevant to the Large Hadron Collider, where we're at very high energies. And we can consider a process like this, which for the experts is a tree-level approximation for a gluon scattering amplitude. Here you can think of this as 2 gluons coming in and 3 coming out. You could alternatively think of this as 3 gluons coming in and 2 coming out, and because of relativity, there's really no difference between those. But you can just kind of think about this object and try to compute it using standard methods. What do you get? Well, here's the final answer. Okay, so this is the full answer I've shown you in its kind of full glory. So if you take out your textbook like quantum field theory and you turn the crank, this is correct. This is like A+, this is the answer. The top smudge here, each of these smudges is some complicated function that involve the kinematics in the problem. There are 5 particles, there's 5 momenta, they all kind of get multiplied and divided by here. Okay, so this is quite complicated. And if you had nothing afforded to you other than the textbook, this would just be all you could get. Now, of course, the story here is this is not the end of the story, thankfully. This is actually hiding an immense simplicity. And to see that, we have to go to a physical configuration. And by physical configuration, I mean an amplitude parameterized by momenta that are not just random, but momenta that actually could correspond to an experiment you would do. And this is a very mild assumption. So in particular, if you had momenta P1, P2, all the way to P5, they should sum to 0 by energy conservation and momentum conservation. That's a simple constraint that you should impose on this. There's other conditions which force these gluons to be physical. And in fact, when they're physical, they must have a polarization. They should be left or right polarized, which means that these H1, H2, which are the helicities, they can take on +1 or -1. Now, if you restrict to something physical, you find something rather surprising. The all plus amplitude, which is just 5 gluons that are all right circularly polarized, it's 0. Okay, so in other words, this expression is a very complicated rewriting of 0. If you look at 1 minus and all plus, you also get 0. You get a little worried. But it turns out that there are non-vanishing amplitudes with 2 minuses, and also, as it turns out, 2 pluses by parity, which take this simple expression, a single monomial. Okay. Here, these angle bracket objects are called spin or helicity variables. And I want to just promise you that there's no dirty laundry hidden in here. These aren't like insane nested functions. These are just, if you like, a reshuffling of the usual 4 momenta you're used to. Okay? So if you just take the 4 momenta and kind of reprocess them, it's these expressions. And it turns out that all amplitudes with 2 minuses or 2 pluses can actually be written down in completely simple analytic forms like this. This was shown by Park and Taylor many decades ago. Okay, so there's 2 points I want to make here. One is that the way that we typically compute is way more complicated than the final answer. And two, it suggests a way that you might compute a different theory whose natural output is these simple objects. Okay, it's enticing because when you see simplicity as a theoretical physicist, you want to find what theory computes this and why it computes this. Okay, what principle dictates this form. Now, this was all for spin 1, which is spin 1 gluon, which is also known as a gauge theory, which is just our fancy way of describing spin 1 massless particles. You can also ask about, say, gravity. Okay? So it's well known that you can describe gravity with field theory. You can talk about scattering of gravitons. Here you envision taking two gravitational waves, interacting with each other in the weak field limit in a flat background, and you can compute that perturbatively. The rules for this were written down by DeWitt and Feynman a long time ago. Here's the Feynman rules. The Feynman rule expression at 3-point, Feynman rule expression at 4-point. It's kind of morally similar to what we saw for gluons, but just even more complicated. If you compute the 4-particle amplitude, you'll find it's thousands of terms. I think it's on my computer, it's like 20 megabytes or something. It's ridiculous. And then it collapses to this expression. Okay? So all other configurations of helicities are 0, and this is the full answer. Okay? So the same kind of miracle is happening, where, again, ST and U are well-known so-called Mandelstam invariants, but again, there's no dirty laundry hidden inside this thing. So what's the origin of this complexity? What's so bad about the way we compute? Where is this coming from? Well, part of the irony is that the complexity comes from something which is celebrated in the textbooks, which is something called gauge symmetry. Okay, so since high school, I'm sure you know that when we talk about, say, voltage, it's not something which is defined absolutely. There's a 0-point voltage which is irrelevant, right? Then you learn later in undergrad that this is kind of lifted into a huge infinite dimensional symmetry, which is called gauge symmetry, where you can take the voltage and you can take the vector potential and shift them in the following way, where theta here is an arbitrary space-time, function of space-time that falls off sufficiently fast at infinity. And it certainly, I remember when I learned about this, I was very skeptical. It seems kind of crazy to have such a huge symmetry in the theory. And there was always this very crucial caveat, which is that every single thing you could ever physically measure in an experiment, like an E field or a B field, actually is completely insensitive to this. Okay? This is something going on behind the stage. Okay? It's some magic which you, by construction, will never see in any physical observable. Okay? Which is already suspicious. And it boils down to the fact that gauge symmetry is not a property of the physics, it's a property of the way that we as human beings have decided to describe the physics. And let me tell you what I mean by that. Well, we know that the laws of physics that we have have various physical principles that we, because of experiments, believe are true. One is Lorentz invariance, and the other is locality. So when we compute an amplitude, we know it's going to be a Lorentz invariant local. If it's not, it's the wrong answer. Okay, that's fine. But as physicists, we want something even more. We want a luxury, and that luxury is that at every single step in our calculation, it is manifestly local and Lorentz invariant throughout. Okay, we want that just manifested everywhere. How do you do that? Well, we know how to manifest locality. We write down an action in a Lagrangian. I just showed you how that hard codes locality from the get-go. In order to have Lorentz invariance, we write down objects with indices like a mu, and we unify the vector potential and the electric potential into one object. Now, the downside here is that this has 4 degrees of freedom, which is too many to describe a photon, which from first principles arguments connected to something called the Wigner group and irreducible representations, the Lorentz Poincare algebra, there are actually only 2 polarizations, and we know this is an experimental fact. 4 is not 2, so we have to invent a gauge symmetry and a notion of gauge fixing in order to remove degrees of freedom. Okay, so in other words, we had a representation which is beautiful for many reasons, but we kind of had too much in it, so we had to introduce gauge symmetries to mod out extra stuff that is not physical. And in fact, that's of course when we actually compute things, we pick a gauge, right? You take your voltage and you set v equals 0 to be something, and then you compute. At the end of the day, we fixed the gauge in order to compute anything, which tells you already that it can't be something super primal in nature. Now, what's the downside? The downside is that since we encode this at every step, the amplitudes know about locality and Lorentz invariance. In some sense, every single Feynman diagram, everything we compute is automatically has both those properties manifest. And we get a lot of terms for that reason. So when you compute Feynman diagrams, you can write down a kind of imperfect measure for how complicated the final answer is. And one imperfect measure, but a measure nonetheless, is the number of Feynman diagrams. And as you go up from 4-particle scattering to 5, 6, 7, 8, you get a huge number. Okay? So here are the Feynman diagrams at 8 point is 34,000 each of which is some complicated expression, some math expression. Now, there's other ways to compute. And one of them I'll talk about are called recursion relations, which do not use a Lagrangian or Hamiltonian, use a completely different perspective. In fact, a perspective that does not encode locality, and in some cases, Lorentz invariance at any step, but in the end give exactly the correct answer, which is equal to this expression. Okay? So these give answers which are mathematically equal, but rather than being 34,000 terms, there are 20 terms of the sort that we saw previously in terms of these spinor helicity variables. Okay, so there's some other way to do things which is much simpler, which I want to tell you about today. Now, what I've told you about here may suggest falsely that this is just some idiosyncrasy of spin 1 and spin 2. Okay? Gauge theories, quote unquote, and diffeomorphism invariant theories, the technical language. But let's say you only care about scalars. You know, I love phonons, they're great. None of this matters for me. That's not true. Let me show you a particularly egregious example of this. So consider the following so-called scalar theory. Okay, so a scalar is just a particle that has no spin, and we can describe its interactions like this. This could be something like the Higgs boson, or like the pion in the Standard Model, or the inflaton, okay, depending on your background. One of those probably connects. And we can write down a Lagrangian for such a hypothetical field with just an infinite number of terms. Okay, so here lambda 1, lambda 2, lambda 3, all the way to lambda infinity is an infinite set of coupling constants and interactions which have no relation. So lambda 1, lambda 2, there's no connection between any of them. Okay? Let's say you took this theory and just started computing. You compute 4-particle scattering, 5-particle, 6-particle. You find something rather surprising. The 4-point amplitude is 0. It vanishes for a physical configuration. In fact, all the scattering amplitudes vanish. You compute all of them, they're always 0. And they're 0 in a very frustrating way. You would have sums of terms involving lambda 1, lambda 2, all conspiring in the very end to cancel and give 0. Okay? Now, this seems like a complete miracle if you don't know some associated paraphernalia QFT, but it's actually obvious in the hindsight if you realize that you can map this Lagrangian to a Lagrangian that has no interactions whatsoever by changing the definition of the field. This is called a field-way definition, where here g of phi has some constraints it has to satisfy, but in general can map this to some nearly arbitrary function g of phi. Okay? So this is not a symmetry of the action. Now, I'm not saying this is a symmetry. In fact, it's distinctly a non-symmetry. It takes this thing to this, and these two things are not equal. And despite changing the Lagrangian, it does not affect the observables, which for the purposes of this talk are the scattering amplitudes. The scattering amplitudes are exactly the same. So this is a non-symmetry, which is also a redundancy of description. And this goes under the name of reparameterization theorems in quantum field theory. What's kind of amusing is that this may seem a little foreign if you know quantum field theory, but it's generic from classical mechanics. Okay? Here's the example. Let's say I gave you a Lagrangian in Cartesian coordinates, okay? And I do a transformation on it that is not a symmetry transformation. It doesn't leave the action invariant. That transformation is to go from Cartesian to polar. Okay, so the action just looks different. Now, if you compute in that new action, what do you get? Well, you get exactly the same expressions as in Cartesian, provided that you carefully remap coordinates, of course. But the way you parameterize your coordinates was irrelevant to physical quantities. Okay? It just doesn't matter if you use polar or Cartesian. Okay? It can obscure things, but it doesn't matter which basis you use. The same thing is true in QFT. Another way of saying kind of formally is that the field is an integration variable, and we can change variables. And as long as we're careful with Jacobians and how we define our asymptotic states, etc., we know that it should not matter what field variables that we use. Now, there's a downside to this, a huge downside, which is that there's an infinite set of Lagrangians that all correspond to the exact same physics. Okay? So in particular, someone hands you a QFT textbook, and they say, this is the Lagrangian for gluons, and they hand it to you. Now you take that Lagrangian and you map it to an infinite set of other Lagrangians by some arbitrary field-way definition. All of these have exactly the same scattering amplitudes. So in some sense, you could have been handed any of these. Now, this infinity to one mapping has the downside that you have no idea whether the Lagrangian you were handed manifests all the symmetries, all the structures that you might care about, or that are present in the theory. Maybe this guy over here, L2, has some symmetry you've never heard of. Okay? In other words, maybe you've been working in Cartesian your whole life when there's really a spherical symmetry in your problem. Now, of course, you could go from Lagrangian to Lagrangian just kind of hunting and guessing. But a much faster way to get to the invariant physical information is to go directly to the amplitude, which is not subject to any of these redundancies. Okay? And that is the kind of essence of why I think progress has happened in the amplitudes program. We don't, for the most part, don't look at Lagrangians, although we'll talk about them at the end a bit. if we just look at the amplitude, it's something whose structure is invariant, and we can learn things from that. Okay, so what's the bottom line? The bottom line is that while actions are incredibly useful for our intuitions, they sometimes miss important physics. And in the remainder of the talk, I want to talk about three aspects where this is missing something, I think, kind of important. So one is the absolute rigidity of certain QFTs. Right? Now, if you're like me, when you learned classical physics, say like electrodynamics, you may have wondered, well, these are the laws of physics we have, but why couldn't it have been different? Right? Why couldn't Coulomb's law have been 1 over r to the 1.7126 rather than 1 over r? What fixed the laws of physics? And certainly when I was young, I was like, well, it could have been anything. And it just turned out that the laws of physics were beautiful. And that's the way it was. Well, it turns out that's not quite true. It turned out the laws of physics we observe, in some very distinct sense, are kind of very, we can't perturb away from them very easily without making them inconsistent. In this sense, there's a very rigid structure that QFTs have. Theories that actually describe our world, which I'll talk about, like the theory of gravity, theory of gluons, the strong interactions, also effective field theories like pions, are actually rigidly constrained by physical principles that can be stated at the level of the amplitude. Okay? And let me just give you, in brief, the basic picture. So rather than start with a theory in a Lagrangian and compute the amplitude, right? That's the usual picture. We start with a Lagrangian, that's the assumption, and then we compute amplitudes. We reverse the logic. Okay? So we instead build the amplitude first. And we build it, as I will show you, from first principles, from just the physics assumptions. And then using the structure of what we get, we then deduce facts about possible theories. Okay? It's a complete reversal of the usual picture. But as we'll see, we'll learn old things and we'll rediscover some facts about QFT that are actually quite familiar, but in a different context. Now, if that was all this was about, it would be much less interesting than it is. And that's because we've actually learned new things which are not at all clear from a symmetry Lagrangian point of view. And I'm going to talk about two aspects in which this is the case. One is that there are hidden dualities which actually connect these quantum field theories. So the theory of the strong interactions, the theory of gravity, even the theory of pions. These are all actually secretly connected to a set of dualities I want to tell you about, which sometimes go under the broad heading of gluon squared equals graviton. I'll elaborate on that later. And then the last thing, maybe in that last couple of moments, I'll discuss some of our work showing how all the theories I'll discuss are actually unified within gravity. Okay, so there's a very concrete sense in which gravity is the mother of all theories when it comes to amplitudes, and I'll tell you about that at the very end. Okay, so if there are not any questions, let me get to the first bullet point here. So as you might imagine, I'm going to assume for this talk at least two physical criteria that I think are well motivated experimentally, at least in a world and energy is much larger than Hubble, which is that there's Poincare invariance and locality. So those are our physical assumptions. Those are what is input. Okay. Now, let me really get to the kind of nuts and bolts of how do you compute the amplitude without a Lagrangian. And at the end, it's kind of deviously simple. Okay. The idea is the following. I don't get an action, so I don't get to even say the words field or anything. All I get to do is talk about the amplitude. So what I do is I write down an ansatz function for the amplitude. I write down a general parameterization of anything the amplitude could be. Okay, now of course, the space of all functions is big, so you need some set of assumptions to kind of pare that down. When I say things like tree-level approximation, that restricts me to rational functions of external kinematics. But it lets you write down, given the right assumptions, like dimensional analysis and say tree level, just a space of functions which the amplitude could be. Okay. Now, this ansatz has a bunch of free parameters, okay, which are unfixed. Now, if you want to impose physical criteria, you just go to the function you built and just demand those physical criteria on those functions. And that will pare down your coefficients to take specific values. Now, when you reach some final solution, there's a number of possible outcomes. Let's say you pare it down to one function which has 19 free parameters. Well, you've discovered the scattering amplitude for a theory with 19 free parameters. Okay. Let's say you've pared it down, and at the end you get a theory with one parameter. Then you've discovered a theory with one coupling constant, say. Last of all, if you write down your ansatz and you find nothing is consistent at all with what you assumed, then you've actually ruled out the theory. Okay? So this is another way of actually ruling out theories in the abstract. Without writing down a Lagrangian, I can deduce that a set of physical principles are mutually inconsistent and no theory is consistent with them. And you can also do that, which I'll show you. Now, if you apply this to the, kind of some of the classic theories, like the theory of gluons and gravitons I discussed, you learn something kind of cute. We, of course, usually think of gluons and gravitons as examples of long-range interactions mediated by massless spin 1 and spin 2 particles, which are self-interacting. Turns out these are the only particles of that type. So the only theories of a massless spin 1 or spin 2 particle with long-range force are the gluon and the graviton. What's interesting is there's some very nice caveats where when you leave 4 dimensions or don't demand a long-range force, you can get interesting other massless spin 2 theories, which I can tell you about. But it's very interesting. There's with the assumptions that we usually think of as defining gluons and gravitons, these are unique. What is the operation that you do? Okay, so let me kind of show you precisely what we do in equations. The simplest amplitude to look at is a 3-particle amplitude, right? It's kind of the simplest process you can imagine of things interacting. Because if I just have kind of one particle going to one particle, that's just called propagation. So the only thing, the first kind of leading order interesting process is 2 coming in and 1 coming in. Now, if I have a 3-particle process and the sum of any 2 momenta is the third, and you get a set of equations here, which I've written in terms of these spin or helicity variables, again, whose definition is not quite important. But the upshot is that this set of equations has 2 solutions, 2 branches of solutions, where either this amplitude is a function of angle brackets or this is a function of square brackets. Okay? And these are the complete and full, as it turns out, non-perturbative functions which describe any interactions of massless particles, of any spin. These numbers here are things that are actually fixed by the spin of the spin and helicities of external states, but there is in fact just a general formula which describes any such particle. So you could put here gluons, gravitons, gravitinos, pions, anything you want, and this will give you that formula. If you apply this to the case of spin 1 and spin 2, you find these following unique formulas for gluons and gravitons. You can check that these expressions exactly match what you would have gotten from Feynman diagrams. And they're much more compact than those expressions you would have gotten. So this is the basic mechanism. You just write down anything you can and sculpt out the right answer, given that you only wanted very minimal assumptions. And I want to emphasize the only thing I've assumed here is Lorentz invariance. Now, you'll notice something already kind of surprising, which is if you take the gluon amplitude and just blindly square it, take the square of it, you get the graviton amplitude. Okay? That turns out not to be a coincidence. Okay, that's something that's going to show up later, and it's the first example of this so-called double copy structure where you square something and get a new object. Okay? This will come back later, and I'll talk about it in length. Now, this, of course, is 3-point, which is super trivial. It's kind of the simplest interaction widget you can imagine. What about 4-point, 5-point, 6-point, higher? Well, here's what you do operationally. You write down an ansatz for 4-point. Okay? You just write down a general function I call A4. And now I need an additional assumption, which I'm going to call locality, which the experts will know is maybe perhaps a strong abuse of nomenclature here. But by locality, I mean the following, at least for this talk. Take your ansatz and take P1 and P2, which are the 2 incoming momenta, and tune them to a very specific configuration. Okay, so just go to some special kinematics. A special kinematic configuration where these 2 momenta essentially go on resonance. Okay, what we do is we say that the intermediate guy is on shell, but it's like a resonant channel. It's like aligning 2 modes to be on resonance. And we have some intermediate guy here. Now, in that factorization limit, this amplitude is singular, just like any resonant process. And this amplitude should decompose into 2 separate processes. The first process is these 2 guys merging together to form this intermediate particle. This intermediate particle then travels some great distance in space-time, hence locality, before it then disintegrates into 2 others. Okay? And the singularity comes from that traversal through space-time. So this places a constraint on A4 that relates it to A3, which we already computed. Okay? So in other words, you take this ansatz and you go to different channels, and then from this you can sculpt out the full A4 consistent with your A3s. Okay? And from this you can build the 4-point amplitude. Now you do this in each order. You can even do this 4-point, 5-point. I've done personally until you can go higher just mechanically. And you can build, for instance, general relativity this way. You start with the 3-point graviton amplitude I mentioned, and just slowly bootstrap your way up and up. And for Yang mills, the same is true. And if you had the kind of mental strength to just keep plowing away, you just build the whole tower. We know this because we can effectively automate this procedure using things called recursion relations, which are essentially mathematical relations which take some endpoint function and relate them to 1 lower number of particles. So we can take endpoint, move it down to n-1 point, all the way down to 3 points. So in this way, we can kind of reduce everything down to these primordial 3-particle amplitudes that we've already deduced from first principles. So in this way, we have kind of an operational definition for the S matrices of theories. Okay? We've built the 3-point, and then we just build everything else from this operation. Now, as I mentioned, we not only can derive old theories that we know of and are familiar with, we can also rule out theories. Okay? So in particular, what we can do is build an A4, which is subject to some set of physical assumptions, which I'm going to plot on the axes of this diagram. Okay? So one physical assumption is, what is the spin of the particles in your theory? Just an input, okay? Which I'm going to call S. So you spin 0, spin 1, spin 2, spin 3. On the y-axis, there's another assumption, which is, I call rho here. Essentially, it's telling you the dimensionality of the coupling constant. Equivalently, it's the number of derivatives per interaction. There's many ways of kind of recasting rho. But basically, it's telling you how derivatively coupled your theory is. That's, I guess, more for the experts. Now, when you assume some rho and some S, you can build the ansatz and just ask, do I get a solution or do I not get a solution? And you build a map of what is allowed and forbidden. So there's a whole forbidden region here and an allowed region, and then some diagonal piece here, which is permitted. Now, what is remarkable is that theories that live right on the boundary actually happen to describe the world we live in. So Einstein's general relativity is here, and the theory of the strong interactions is here. And they live right at the cusp of being excluded in the sense that they're almost excluded and inconsistent. And that may seem kind of surprising, but it's actually obvious in hindsight. When we talk about GR, it's a one-parameter theory, G Newton. When we talk about the strong interactions, it's got one parameter, which is alpha S. Now, of course, we can imagine adding things called higher dimensional operators, corrections to those, and those all live kind of deeper inland in this theory space. But things on this boundary are kind of the simplest possible theories, because if we constrain them any further, they wouldn't exist. Yeah. So it's kind of remarkable to see them all kind of aligned in some unifying picture. Okay, so this is the map of theory space. Again, I want to emphasize there was no Lagrangians involved in the making of this plot. It was just from first principles, constructing the observable and deducing what theories could have produced that observable. Now, this operationally gives us a definition of a large class of theories, basically using on-shell recursion relations, including this big class. But there's kind of a missing piece here that you might be aware of if you know anything about how modern physics works today. There are a set of theories called effective field theories, which are very powerful, pragmatically useful, and also have very interesting formal structure, which are missing from this list. Okay, so these EFTs are really kind of ubiquitous at this point. They were originally devised in certain contexts, like to describe superconductivity, with the theory of the strong interactions. So the theory of pions, if you know about it, is an effective field theory. But at this stage, they've been extended to, these kinds of ideas have been extended to cosmic inflation, large-scale structure, dark matter, EFTs, fluid dynamics. The basic idea is to accept that you do not know the full theory. You do not know all the intricacies of the full theory. And you want to write down an effective field theory which has some limitations. It has some regime of validity which you know the boundary of. Nonetheless, these effective field theories can be very predictive, especially when there's symmetries in the problem. So again, I want to kind of get a little more concrete than this abstract picture. So let me show an example from classical mechanics. Okay? In classical mechanics, you could study a ball in a wine, potential that forms the kind of bottom of a wine bottle. Okay, so there's kind of a maximum here, and then it rolls up and goes down and up, and this whole thing has an azimuthal symmetry. Okay. So obviously, if you kick this ball around, it is a two-dimensional system. It can move in two directions. However, at low energies, very low energies, this thing settles to the basin. Okay? It effectively becomes one-dimensional and lives on a circle. There's a theory that describes this circle degree of freedom, which is parameterized by a single angle, phi, let's say, which moves around in the circle. And it's a very simple, lower dimensional effective field theory, which describes everything at low energies. Now, of course, everything about the full theory is somehow secretly encoded in that, and we'll discuss that a bit later. But this is a simple theory because there is a symmetry. Okay? Because I started with an azimuthal symmetry, this basin was a perfect circle, so I could make predictions in the EFT. If this was some crazy potential, it would be much harder. So you can already see that kind of the way we think about effective field theories that are predictive intrinsically have symmetries or symmetry breaking in some sense. And naively, that seems like a huge Achilles heel to everything I've said. I've told you I've forgone Lagrangians. I don't get a Lagrangian. I don't deserve one. So instead, what do I use? Symmetries are things that act on fields, right? You asked about a symmetry of a Lagrangian. What can I replace it with? Well, it turns out the thing you replace it with is something called infrared structure, which is just a fancy name for the properties of amplitudes when you take particles to be very low energy. And this is actually something with a long prehistory, but let me tell you about it. In fact, in the seminal work of Adler, this was observed already in the pion Lagrangian, but it's this basic idea. We want to take something called a soft limit, where you take an amplitude, you take the momentum of one of the particles, and you send it to 0. Okay? Here, we're relativistic, so momentum is energy. We just send both of those to 0 at the same time. By continuity, we get a function which, at leading order, is p to some power sigma. And since I'm working at tree level, this is some integer. Now, something interesting happens when sigma is positive. It basically means that this amplitude vanishes in the soft limit, which means that the probability of that process occurring vanishes in this limit. And this is something that was discovered to be true for the theory of pions in the chiral limit. Let me show you how this works for this example I mentioned. So we define this effective field theory of a ball at the bottom of a basin. As I told you, it's described by an angular variable, which just tells you where it lies on the circle. Now, without doing any work, we know the Lagrangian for this variable. Why is that? Well, this thing has a rotational symmetry. Right? I could just take an angle and again shift it by a constant. So whatever Lagrangian I write down should be invariant under shifts of the angle. And you'll realize that the only Lagrangian you can write down that has that property is something which is a function of a derivative acting on the angle. Because if you shift the angle by 17 pi over 12, then the derivative will cancel it, and it's an invariance of the Lagrangian. Okay, so this is the way we think about this from a Lagrangian picture. There's, of course, an infinite number of terms Cn, parameterizing the fact that this wine bottle could have some crazy shape. Who knows what shape it has up here, but that's all encoded inside these Cn's. Okay? And there's an infinite number of free coupling constants that we don't know. Now, in the standard picture, we build this from that type of symmetry argument, and then we compute an amplitude. And you'll find trivially that the amplitude scales with 1 power of p, which is obvious because there's one derivative on every phi. So if you make a phi soft, it just pulls out this derivative, and that's that 1p. Okay, so it's kind of obvious why it should have this property. What is slightly less obvious, or slightly less trivial, I should say, is that you can do the reverse. This is a two-way street. If you write down an ansatz, like the one I mentioned, and you demand this as a constraint, that it vanishes when p goes to 0, what you'll find is an ansatz which is pared down to some set of coefficients Cn, which is an infinite set, which is exactly in one-to-one correspondence with these terms. Okay, so in other words, you can rederive this Lagrangian in this way. Now, this is not at all surprising. It's in some sense very trivial. Something more magical happens if you up the ante. Okay? So let me say I demand an even softer limit. Okay? So I take this class of theories, and rather than demanding this goes as 1 power of p, I demand 2 powers of p. So that means the one term needs to be 0, and the order p term has to be 0. So that the first non-vanishing term is p squared. Well, you do this, and you find that the couplings are actually all fixed in terms of one final coupling. So these Cn's all end up becoming constrained up to one free parameter I call lambda. If you look at these numbers, you'll recognize them as a somewhat famous Taylor expansion, which is the Taylor expansion for a square root function. And it turns out that this Lagrangian already had a name. It's called Dirac-Born-Infeld theory, and it describes the motion of a brain in an extra dimension. Okay? Completely different backstory here, where, well, just to give you some context, the idea here is that in an extra dimensional theory, we think of our 4 dimensions that we know and love as some kind of surface inside a higher dimensional plane. And that plane is moving in some other space. This phi here is parameterizing its coordinate in the other space. And since there's a translation invariance in that space, this thing has a shift symmetry, but it also has so-called non-linearly realized Lorentz boosts, which are also good. Now, as I said, this is something that comes out of string theory, extra-dimensional models, which has a very beautiful story. But here it came from a very modest assumption about the amplitude. Yeah, a very natural assumption you would make, which is, well, what happens if we just ask for an even softer theory? Now, you can do this procedure where you map, again, the space of all theories. Here, the y-axis is, again, the rho parameter, rho-type parameter I mentioned before, which is the dimensionality of the coupling. The x-axis is these sigmas. And you find, again, a bunch of different theories. Actually, this cusp point here was the theory that, well, when we found it, we didn't know what it was. It obviously had some significance because it was at the same cusp point as where gravity was in the other case. We wrote our paper and said, hey, there's some set of amplitudes that live here. And I think maybe like a month later, Kurt Hinterbichler wrote a paper showing how this is actually a special point in a theory called the Galilean, which was actually pioneered here at NYU under the name DGP by Diwali Parati and Gabadadze. And it's some kind of super enhanced version of it, which has an even better soft theorem. If you know anything about the history of string theory, you'll know this is not the first time something like this has happened, where we kind of found the observable before the theory. This is a much more minor version of it, but it shows the kind of power of the reasoning. Don't start with the Lagrangian, just build the theories. And you can build other theories kind of deeper inland in the usual way. Now, because we can build them, we can build so-called recursion relations for all the theories I mentioned. This puts the pions, dBi scalars, and Galileons, which are also things that might be relevant to cosmology for kind of phenomenological reasons. All of these are now on the same footing and equally constructible. So we can build their full S matrices using these methodologies by automating this procedure in the same way. OK, now, hopefully you've anticipated that I've drawn these two diagrams in a very kind of close-looking form. And that's because I want to emphasize that not only are these kind of edge theories special because they're maximally constrained, they're all one-parameter theories, they also have the unique property that they're actually connected in very intricate ways with each other through various dualities, which I want to tell you about next. Okay. So let me tell you about these hidden dualities. Now, for the most part here, I've only talked about kinematics, right? I've talked about momenta, and I've ignored all the other kind of interesting labels that an amplitude can have. As it turns out, gluons don't just have kinematic labels in the sense that, of course, they have momenta, but they have another label which is called color. And if you know nothing about it, you can just think of color as basically a species label on the gluon. There's some number of gluons in your theory, and different ones of them can interact in different ways. So there's a color index and a momentum index. The three-particle amplitude has actually two pieces. One is the kinematic structures that we've been talking about up till now. And another piece is the color structure. And the color structure basically tells you which gluons talk to which gluons. Okay? Which species of gluon talk to which species of gluon. Now, given this simple product, one can try to extrapolate wildly and say, well, wouldn't it be great if there was some duality between color and kinematics? Because this amplitude is just the product of the two. What if I just interchange these two functions, which I've suggestively drawn in a very similar way? Okay? This object and this object show up together. What if there's actually duality that connects them? Well, this kind of naive initial first step is actually destined to failure because color and kinematics are just at some level very different. And you can see this because of a basic identity that fails in the case of kinematics. So this identity is called the Jacobi identity. It's something which I think you should know as something from mathematics, the three-vector calculus. You take a sum of these various cross products of three vectors, you get 0. This is, as you know, just an identity. Turns out that those color structure constants satisfy the same type of identity. Okay? And it's an identity in the sense that it's just mathematically true. You calculate all the terms, and you get 0 on the right-hand side. Now, if you do the same thing for the kinematic piece, basically the functions we just computed, you don't get 0. You get a non-zero answer, which already tells you there's, just right out the gate, there's a difference between color and kinematics. Now, fortunately, people did not stop at that point. In the seminal work of Zvi Byrne, J.J. Carrasco, and Henrik Johansson, they kept trying, and they found something rather miraculous, which I want to show you at 4 point. So consider a 4-particle gluon amplitude. You can, on general grounds, write it in the following form, where the C's here are just the color factors I mentioned before. So these are the things that satisfy the Jacobi identity. So this triplet CS, CT plus CU, it sums to 0. And this is automatic, since it's just a math identity. These n's, ns, nt, and nu, contain all the kinematic stuff. Okay, so if I, for instance, were using Feynman diagrams, these n's would contain inner products of momenta and polarizations. Now, what they showed, rather amazingly, was that there's always a form of the amplitude you can write down. In other words, starting from an amplitude, you can always massage it into some form such that ns plus nt plus nu equals 0, thus satisfying the same identity as color. Okay? It seems like kind of a strange, clunky set of instructions. But let's say you do that. Okay? I should say it's semi-trivial that you can do this at 4 point, but the fact that you can do this at 5.6 point and higher in general is surprising. It's a little non-trivial that you can even find a form such that these have this kind of parity. But then they conjectured something called color kinematics duality, which is that since these things satisfy the same algebraic identities, surely there's a duality between them, and you can substitute one for the other. So let's say you do that. Right? You've gone to this form. And now you take the color factors and just blindly replace them with these kinematic numerator factors. Well, what do you get? Well, you replace all the C's with N's, and you get this expression. This is a new object. This object has no color, because color's been removed. And in fact, it also has slightly different interactions because the kinematic part has been squared. Turns out that this is exactly the 4-particle graviton scattering amplitude we saw before. Okay, so I don't think this should at all have been obvious why this had to happen. I mean, you could have squared this and just gotten garbage, just nothing. But instead, you get literally the 4-point graviton amplitude. Okay? This is not in any of the instruction manuals for quantum field theory. It does have some known kind of ancestry in string theory under something known as the KLT relations, which have to do with open string, closed string duality. But it's actually something much more general. The picture here is that basically you can take a gluon amplitude and square it to get a graviton amplitude, where this multiplication is a very precise mathematical statement. This double copy, so this fact that you can square to get the correct amplitudes in another theory, has been proven at tree level, so that is to say at all orders in numbers of particles, verified at loop level, and also it's now so mature that it's being used in high loop calculations actually as a tool. In fact, that's how it was discovered. On top of that, it's actually also more generic than just a property of gluons and gravitons. It's a property of many QFTs where the kind of basic workflow is you take an amplitude of spin S1 with some multiplicity factor or a species index. You take another amplitude with spin S2 with, again, a species index. And then you multiply them to get a new amplitude with spin S1 plus S2 that has no multiplicity index. So gluon, gluon, strip off color, and you get a graviton. We showed later that if you take a pion and another pion, they have flavor structure. You do exactly the same operation. In fact, it's the same KLT relations for string theory, exactly the same. You apply the same relation, and you actually get the amplitudes of the special Galilean. Yeah, this is proven. Even more bizarrely, if you take a gluon and a pion, okay, these guys kind of have no reason to ever be in the same sentence, usually. This guy's species index is color. This guy's species index is flavor. You strip off all of their species indices, multiply them, you get the amplitudes for Born-Infeld theory, which is a very famous nonlinear extension of electrodynamics. Okay. So these things all have kind of names and show up on HEP-TH for completely different reasons, but they're all appearing in this kind of web of dualities.
So the spin S1, S2 have to be less than
Um,
something, right?
Good, yeah, good. So you could add, that's an excellent point because as I showed in a previous figure, if the spin is too large, in fact above spin 2, there's no consistent interacting massless particle. So that's why it's very difficult to actually come up with consistent theories that have a multiplicity index with such high spin. So for instance, having a colored spin 2 object, that's where the difficulty comes in. But indeed, you can actually derive some of these consistency conditions by showing that there's nothing you could put on the left-hand side that would square to a massless spin 3 interacting theory. Now, this was all at the amplitudes level, but I did want to kind of take things back to the action. And I want to emphasize that not all this is just kind of abstract statements about amplitudes. We can actually take some of these statements back to the Lagrangian, where maybe your intuitions are a little more well-formed. Okay? And I want to just mention one thing here, which is that this structure, this double copy structure, actually tells us something about gravity. In particular, I've told you that a graviton amplitude is a product of gluon amplitudes. And of course, an amplitude is a Lorentz invariant. Okay? So this gluon amplitude is Lorentz invariant. This gluon amplitude is also Lorentz invariant. Okay? So product of two Lorentz invariants is separately Lorentz invariant. It has two separate Lorentz invariances. Of course, this is confusing because we think of gravity as having one sole Lorentz invariance. At least, and here I mean gravity in terms of gravity waves in a flat background. That's why I'm talking about Lorentz invariance. And here it seems like it's become two. Now, what's remarkable is you can actually manifest this double Lorentz invariance at the level of the Lagrangian. So what we did is we took the Einstein-Hilbert action, and we basically did an arbitrary field redefinition and gauge fixing, completely free parameters, all of which doesn't affect the physics and amplitudes, which you can check. And then we asked, is there any choice of those gauge fixings and field bases that you can make this manifest? And there is one. You can write it down. It's actually a very compact expression. And what you get is a Lagrangian that describes gravity, which has two Lorentz invariances. So in particular, when you compute Feynman diagrams, every Feynman diagram off-shell has two separate Lorentz invariances. When you compute the final expression, you actually get an object with two diffeomorphism invariances, two separate word identities on the indices. So you can kind of learn something cute about gravity kind of by reverse engineering some of these statements.
And that's all in metric formulation, never used any Firbeins or anything.
Yes, that's right. This is, in fact, the degree of freedom is just a general tensor with two indices. Yeah. In fact, it's a very elegant looking object. It looks a little bit like the chiral Lagrangian, in fact. I could show you, but yeah. There's no mention of in this picture of kind of the beautiful geometry behind it, because we're kind of foregoing that picture here. Now this is all kind of maybe haughty-taughty formal theory. You could ask, is there any pragmatic benefit from this? And there is, well, not yet a benefit, but a goal that we have in the Amplitudes program, which is to apply some of these ideas to something that would be relevant phenomenologically, and a very clear kind of natural candidate for that is LIGO. Right? So famously, there's been the discovery of gravitational waves, a real tour de force of theory confirming Einstein's relativity. If you think about the way this is computed, there's many methods, some which are kind of iterating Einstein's equations. The ones that are closer to quantum field theory, like things like non-relativistic general relativity, these things are at the very heart, basically, Feynman diagrams, using something called the post-Newtonian expansion, which is an expansion in small velocity. And you just do perturbation theory. And if you're interested in the orders that have been computed up till today, which is 4 pn, fourth order in the post-Newtonian expansion, this actually corresponds to as much as 4 loop diagrams, which is very complicated with Feynman diagrams. Now, what I and many others have been attempting to do is take some of the magic in the amplitudes and transport it to statements about that would be relevant to LIGO. And the basic idea is that, well, Yang-Mills amplitudes, gluon amplitudes are much easier to compute than gravity amplitudes. Maybe if we square them, we get simple expressions. And of course, that's not the end-all and be-all, because of course LIGO doesn't care about amplitudes. It cares about things like conservative potentials and radiation reaction. So we have to do that mapping too. And in a recent paper with Ira Rothstein and Mikhail Salon, we showed how basically mapping, using unitarity methods in amplitudes and merging them with EFT methods, you can actually get new results for the post-Minkowski expansion. So in some sense, all orders in velocity, 2 orders in g Newton, for the conservative potential between 2 binary and spiraling black holes. I wanted to say that just to emphasize that this story is not just about n equals to 4 supersymmetric gluons. We can actually make statements about real-world massive states like black holes interacting to Einstein's relativity. And we put out this paper, I guess, maybe a couple weeks ago, and we also have checked that it matches all known 4pn, up to 4pn known results. And it can be used as a check for higher pn because it has all orders of velocity. So up till now, I basically have discussed the double copy as kind of a thing handed to us as true, and it's been checked. So it's a true fact about amplitudes. I have not at all told you why the double copy is true, or why it seems ubiquitous or so common amongst theories. I showed you the cases of pions, gluons, gravitons. There's also color kinematics duality for QCD. For theories with n equals 0 to n equals 8 supersymmetry. There's a whole soup of different theories, Einstein-Maxwell theory. All these theories, Einstein-Yang-Mills theory, basically if your theory has a name, there's like a fair chance that it's on one side of one of these dualities. But it's still not apparent to me why it's true from kind of a physics standpoint. It is true, but what was the physics argument for why it's true? I'm not going to give you that answer here, but I'm going to give maybe some partial evidence for why it should be generic, connected to my last topic, which is unification of all these quantum field theories. Okay? And the upshot is actually very simple. Okay? Imagine someone handed you all the amplitudes in gravity. Okay? They just had an oracle, and they computed, say, all the tree amplitudes in gravity, and they just gave them to you. It turns out there was a mechanical way to sculpt out of that mathematical object all the amplitudes of every theory I've discussed so far, including gluons, pions, galileons, and so on. Okay? And it's through a set of operations denoted here by blue and green arrows. Just to show you that this is not some vague thing, it's a very actual simple operation, which you could even go to your office and do after this, which is to think of the amplitudes as abstract functions of kinematic invariance. So think of A as just a function of inner products P.P and P.E and E.E. Okay? These are polarization vectors, which I'm returning to, and I'm adding also momentum vectors. Now, if you think of the amplitude in this form, let's say a gluon amplitude, you can apply certain differential operators on this A, and the claim is that these blue and green arrows turn these particles into other particles. There's some set of rules you need and ordering in which you apply them, but by applying these sequentially, you can get all of the other amplitudes in this theory, giving you what we call the unified web of theory. It's completely mechanical. Now, I should say, this is not conjectural. We can just check this. First, we found this, checked it at 8 point, up to 8 particle scattering, and then we proved it using recursion. So it's just a fact about amplitudes. Now, this again is purely at amplitudes level, but I would argue that it actually gives some insight into maybe some of the underlying physics, which is that since from gravity you can get everything else, it suggests that every property of gravity should be inherited by its descendants through this operation. Okay? So in fact, here's one property of gravity. Gravity is the square of gluons. If we apply this operation, you can just see mechanically that you get pion amplitude squared equals Galilean amplitude. Okay? In fact, there's a whole kind of side story here I could tell you offline, where we've now taken this operation and mapped it to a Lagrangian. So what we've done is you can take the Yang-Mills classic Lagrangian from your textbooks, apply an operation at Lagrangian level, which is a very peculiar version of dimensional reduction, to get a new action for the chiral Lagrangian, which has very bizarre properties. This chiral Lagrangian is purely cubic, okay, which already sounds strange if you know anything about how pions work. It's purely cubic. It has some auxiliary fields that come from the full theory. It's purely cubic. It doesn't manifest even bow symmetry of the pions. But nonetheless, it has other beautiful properties, which is that it actually has color kinematics duality as a symmetry. Okay? It's a symmetry of this actual Lagrangian, which I don't have time to tell you about here, but I could tell you about.
Was that known by itself, that Lagrangian?
No. We wrote it down earlier, actually. So we had built this Lagrangian in a completely different way, essentially by starting with amplitudes obtained from double copy and reverse engineering this Lagrangian. So first we reverse engineered it, and then we discovered that you could also get it directly from Yang-Mills. And there's some very nice structure here. In fact, I could let me just allude to one nice fact about this, which is that there's kind of a perennial question here, which is when I talk about color algebra, we all know what that is. It's some kind of algebra relating to the identities that color factors satisfy. If I talk about the Jacobi identity for kinematic structures, it suggests the kinematic algebra. What is that algebra? And in this picture, you see that the kinematic algebra of this theory descends exactly from the Lorentz algebra, the Poincare algebra of this other theory. Okay, so there's in this sense, that there's a connection between the kinematic algebra and Poincare, which I think is somewhat enticing. So this is one aspect.
What is that Lagrangian a coset of? If you're doing a pion.
Great, yeah, it's you can't even think of it in terms of that language. So it's not something you build from CCWZ. I can show it to you. You'll see how it's completely bizarre. It's not something you would write as a symmetry breaking type of Lagrangian, in part because it doesn't even preserve bow symmetry of the pion. Now, of course, the amplitudes do, and it gives all the correct answers, but it doesn't have that kind of built. I can show you that. Now, other things that are inherited are things. I'm being a little sloppy with the nomenclature here, but general covariance of gravity, which I would say at the level of amplitudes you can think of in terms of things called soft theorems, things called the Weinberg soft theorems. It turns out these soft theorems, which encode general covariance, gauge invariance, and these infrared zeros, all map onto each other. Okay, so here for the experts, the Weinberg leading and subleading soft theorems in gravity map to the leading and subleading soft theorems in QED, the famous Kroll-Burnett-Low soft theorems, which then map onto the Adler zero and the sub-Adler zeros that were discovered recently by Frank Chaza. So, and collaborators. So there's also kind of an interesting unifying connection between all of these, which again, I don't think we fully understand. Okay, so I think I'm probably coming near to the close. Before I finish, I did want to emphasize that what I've showed you today is really just a very idiosyncratic slice of what is a very quickly growing and exciting field. There's kind of any number of small miracles that we kind of keep seeing. I'll just mention a couple. For instance, there's things like the CHY scattering equations, which are magic formulas, compact expressions, which give all the amplitudes in every theory I talked about. Okay. Or things like the amplituhedron, which you may have heard about in the popular press, which gives a way of interpreting scattering amplitudes as volumes in various abstract spaces. So this is kind of a very interesting business where there's all these facts that we know are true about amplitudes, but we don't know why they're true. So it's a field where there's a huge imbalance between numbers of answers and questions. We know lots of structures exist, but they don't really have an explanation yet from the kind of conventional symmetry point of view. There's some miracle that's occurring that's somewhere between when we start with Lagrangians and get to the scattering amplitudes, which I personally I'm spending a lot of my time trying to understand, and it's been really a joy to work on. So that's all I have to say about today, and thank you for your attention, and stay tuned.
Question, please. Massimo.
There were no masses in your story, right?
Yeah.
Everything was massless.
That's
so,
right.
All this. What happens to this beautiful structure when you?
Right. So I would say for the double copy side, these square relations, there's something very special about massless, which makes it easy to implement and nice. For the story that involved just constructing amplitudes, that can all be done with masses. So recursion relations have been done for massive theories. Actually, Nima had a paper where he built spinor holicity for massive particles. So there's kind of two different tracks here. There's the new structures discovered, which kind of, it makes sense, should only apply to theories that are massless because they're nicer theories. We know that they have more symmetries in general. But the fact that you can still construct massive theories, I should also emphasize that this isn't just, it's not just massless theories that we can build using these methods. They just may not have as many of the nice properties that massless theories have.
More questions? Yeah.
So when the supersymmetry fit into the double copy, will the gluino marry the gluon who give the gravitino?
Yeah, so it's basically that kind of just addition. Yeah, I think it's like n equals 1 cross n equals 1 is n equals 2. N equals 1 cross n equals 4. There's some multiplication table of supergravities. It's a rich table that if you look through any of Henrik Johansson's very nice talks, you'll see it's like a whole list. And occasionally you have additional matter that you include, but it's a complete mapping that's understood. It's very, well, it's very interesting. It's perhaps not surprising, I should say, that it works in supersymmetric theories. I think the logic is if something works in a non-supersymmetric theory, making it supersymmetric will only make it nicer. So I would expect things to not fail by making things supersymmetric, right? Because supersymmetry makes a simpler theory, not a more complicated theory. But yeah, there's a whole kind of table of supergravities that have been studied. Now they've extended to conformal supergravities and all kinds of different branches.
More questions? Yes.
As far as I can tell, you talked exclusively about tree level amplitudes.
Mm.
Can you say something about loop level amplitudes, or how
Sure.
do things change?
Yeah, so actually the whole loop side of the story is also fascinating and deserves its own talk. There is a way to build amplitudes at loop level called generalized unitarity. This is something, again, pioneered by many of these individuals like Weber and Dixon, David Kossauer. And the idea is to basically, it's a souped up version of the optical theorem, where you don't just cut two legs, but you cut many legs. And it allows you to relate integrands at loop level with products of tree amplitudes. And there's a systematic way of building these loop integrands from tree. And this is exactly what they use to determine things like the finiteness of supergravities at very high loop, together with things like double copy. So yeah, so it's very mature also in that direction, but I just don't have time. I should say also, there's another place where the double copy is also very enticing, I didn't mention, which is at the level of classical physics. So there's something called the classical double copy, where if you take Schwarzschild in Kershield's coordinates, very nice set of coordinates for black holes, it actually is exactly the square of a monopole solution in ENM. So there's this very enticing kind of double copy structure that exists at the level of classical solutions where people studied various variations of this. I don't know, personally I'm not sure if this is kind of continuously connected to the actual amplitudes double copy. It's of course kind of apples and oranges, but it's certainly well, something worth thinking about, I think.
Thank you, very interesting. Cliff will be here for half hour, upstairs 10:45, wine and cheese, everybody's invited, and also he'll be here tomorrow, right? So let's thank Cliff.